Crystal oscillators explained. From DC bias to stable frequency. Chapter 2. DC biasing, preparing the transistor to oscillate. Before any oscillation can happen, the circuit needs preparation. DC power doesn't create the signal. Instead, it places the transistor in the correct operating region. Without proper DC bias, amplification, and oscillation simply cannot exist. A transistor acts like a controlled valve. A small change at the base controls a much larger current flowing through the device. This ability to control current is what makes amplification possible. And amplification is essential for oscillation. The base voltage is set by a simple voltage divider. Resistors R1 and R2 create a stable DC voltage at the base. This voltage does not set frequency. Its only job is to correctly bias the transistor. The base emitter junction behaves like a diode. In a silicon transistor, this junction turns on at about 0.7 volts. That's why the emitter voltage naturally sits about 0.7 volts below the base. This relationship comes from physics, not from design choice. The emitter resistor converts voltage into current. As the emitter voltage rises, current increases. If temperature or transistor gain changes, the resistor automatically pushes back. This negative feedback makes the bias stable and predictable. DC and AC signals do not see the circuit the same way. For DC, the emitter resistor remains in the path and stabilizes current. For AC signals, the capacitor bypasses the resistor. This keeps the DC bias stable while restoring high AC gain. Now let's trace the DC current path. Current flows from the power supply, through the inductor, into the transistor. It exits through the emitter resistor and returns to ground. The inductor allows DC to pass while blocking high-frequency signals. DC bias prepares the transistor to operate in its active region. The base voltage sets the emitter voltage. The emitter resistor sets and stabilizes current. With the DC conditions correct, the circuit is finally ready to oscillate.